Yes, must be. Well done. Okay, so I promised to switch to English today, and we're going to have a popular lecture from a famous problem in kinematics called the Brachistochrone Problem. The words Brachistochrone come from Greek, and in a way of a literal translation, mean shortest time. Now, this was a famous problem during the time of Newton, so second half of the 17th century, and it was originally posed by one of the famous Bernoulli brothers. You may have heard of the Bernoulli equation. So there was more than one Bernoulli. The Bernoulli equation comes from Daniel Bernoulli. This is one of his brothers, Johann Bernoulli, and another one of those brothers, Jacob Bernoulli, has also solved this problem and got into a big fight with his brother over it. We'll get to that. So those were some romantic times, and when somebody posed a problem, then they wrote a letter to the Royal Society in England, or some kind of scientific society in France, in Germany, to be read out loud to everyone. So I'm going to do that. I, Johann Bernoulli, address the most brilliant mathematicians in the world. Nothing is more attractive to intelligent people than an honest, challenging problem whose possible solution will somehow bestow fame and remain as a lasting monument. Following the example set by Pascal, Fermat, etc., I hope to gain the gratitude of the whole scientific community by placing before the finest mathematicians of our time a problem which will test their methods and the strength of their intellect. If someone communicates to me the solution of the proposed problem, I shall publicly declare him worthy of praise. The problem he posed was the following. Given 2 points A and B in a vertical plane, and this blackboard will be our vertical plane, what is the curve traced out by a point acted on only by gravity, which starts in A and reaches B in the shortest time? That's it. That's the whole problem. So the question is, which way should I go in order to minimize the time required to descend from point A to point B, assuming we have gravity? Of course, to obtain any of these curves, for the body to move on any of these curves, we need to put something below it, some kind of a shaft of some kind, which means that gravity is no longer the only force in this body. We certainly have the reaction, the force of reaction of the shaft, and we probably also have friction. But this is imagined as an intellectual problem, so we'll disregard that. Okay, so after this question was posed, mind you, he already knew the answer. That's why he posed the question. Newton felt very challenged. He was working at the Royal Mint at that time. He was a national treasurer for England, so he was making money. And after a hard day's work, he came home at 4 p.m., I believe, so the story goes. He found the problem. Somebody gave it to him, of course. And he wouldn't get up until he solved the problem. Now, the time frame that Bernoulli posed for a solution was 6 months. 6 months. Newton was done in 12 hours. So by 4 a.m. And he sent an anonymous solution to the Royal Society, which was immediately recognized to be his solution. I think the person that received it said, I know a lion when I see its claw, something like that. So referring to the fact that one of the Newton's family emblems was a lion or something. So beware that in this time there was no differential calculus. So they didn't know about derivatives, about integrals, They didn't know about differential equations, nor how to solve them. Using modern methods, in fact using Newton's methods, which he did not use in his solution, I can show you the way to solve this problem using differentials and integrals. I will not show the entire procedure of how to do that because it's a bit intricate, a bit complicated. You will need to listen to classical mechanics, and you will need to listen to matematičke metode fizike, mathematical methods in physics, to gain appreciation of all the steps that are needed here. But the idea is this. Suppose you have any 2 points anywhere, and that this holds true, so that they're acted on by gravity. They can even be posed as a problem of this kind. So let's say we have 2 points in a horizontal plane, and then we have some kind of a curve traced out by the moving point or a moving ball or whatever. And the question is, what is the time required to get from here to here? This is the time we need to calculate because we will need to minimize it, get the minimum time. So how would we do this in kinematics? Well, we know that in kinematics, I'm not going to write any vectors here because everything we do is one-dimensional. So in kinematics, v velocity is defined as ds over dt, where we already assume we know what a differential is, so what ds and dt mean. And if I want to extract dt from this to calculate the time, then I can write this as dt equals ds over v. And I perform an integration to obtain the total time. So to get from dt to the total time, I need to place an integral here. With bounds, a bounded integral. So let's say the time starts at 0 and the total time is capital T. But if I put an integral here, I have to put an integral here. Not quite sure which exactly borders I should put here. Probably s equals 0 and s equals the total displacement, since the differential here is in ds. But it's not a nice way to write this. So the way we do this in modern physics is we try to write everything as a function of a single variable that is clearly defined in the system. So what we usually do is we set up some kind of a coordinate system. Let's call this y pointing down and x pointing to the right. We will allow ourselves to use some of the results that were already known at this time. One of those was Galileo's result, and the result that you know from mechanics, from the law of conservation of energy. I know we didn't come to that during our lectures, but we will, and I assume you do know it. So assuming that the particle moves under the force of gravity and there are no frictional forces, energy must be conserved. And if energy is conserved, then the velocity is identically equal to the square root of 2gy. This is the law of conservation of energy. So this we're going to plug in here for the velocity. Okay, so now we have one variable here that is y, which is the coordinate pointing downward. And we have ds. ds is a small element of the trip that the point makes. If I draw it like very, very, very zoomed in, then this might be ds. That one is pointing slightly upwards, which I did here. But ds, I can write with the help of dx and dy, like this. Using Pythagoras Theorem, ds squared equals dx squared plus dy squared, or in other words, ds equals the square root, the positive square root, because ds is always positive here, of dx squared plus dy squared. Okay. Now we do another manipulation here. We will extract dx from these two terms. So let's do this. Let's say I write dx squared Then from the first term I have only 1, and from the second one I have dy over dx squared, like this. Dx squared I can take out from this square root sign. Dy over dx I can recognize as the derivative of y with respect to x. And in total what I get is the square root 1 plus y prime squared. The prime designates the derivative over x. And let's not forget dx on the outside. So the total time now becomes something like this. Instead of ds, I'll write this. 1 plus y prime squared. That, for we will write, let's extend this square root like that. 2gy, like this, and then dx. Dx comes from here. And the boundaries now have to be with x starting from 0 to some x pi. 0 and x pi. Okay, and this is the way to calculate the time required to get from point A to point B. This, by the way, is related to one of the problems, conceptual problems, posed to you in one of your assignments, where we have shafts of different shapes, and then we have some balls which we will consider points. And the question is, if I put 2 balls here at the beginning and release them, which one reaches the other end first? So this is exactly this. This is the calculation of this time. Now, what we might conclude, for example, from the law of conservation of energy, if there is no friction, then the velocity here at the beginning of motion is the same as the velocity at the end of the motion, because they're on the same height. Also, I can conclude that this ball here is on average faster than this ball. Why? Because it is lower in the gravitational field. So the lower it goes, the higher velocity it has, and it's low more often than this ball. So on average, it needs to be faster. But also it has to traverse a longer path. So it's not clear. What you could do is you could try to calculate. You can always try to calculate. I'm not going to calculate completely, but let's, for example, take this simple shape, which we might model like this, like that, and say the ball starts from here, which will be our x equals 0, and then ends up here, which is x equals L. And if you define a coordinate system like we did, x and y, in real world, you need units, so we would put x in centimeters, y in centimeters, and so on. And then this is very, very simply described by a linear function. So this is just a descending linear function. This is a constant linear function. This is a ascending linear function. So the total time would be, let's call this xa, the integral from 0 to xa. 1 plus y derivative squared. Now we need to write y of x for this thing here. After we write y of x, we know the derivative immediately. And if we know these two things, I can plug them in there and obtain an integral, simple integral. And I would reach the necessary time, and then the time here, and then the time here. These are all simple motions, so you can do it without the integral. For the second case, you would need a slightly more complicated function, so probably something that goes as a cosine, I guess. But tell me, what is your prediction? Where will the ball reach the other end sooner? Any prediction?
I think they were at the same time.
Same time, okay. Perfectly balanced prediction.
The farther.
The what?
The farther.
The one closer to me?
Yes.
That one arrives sooner.
Yes.
Okay. We're only liking the third prediction. That's obvious, and that this ball arrives sooner. So let's see. I'm going to release the balls. I'm going to let them travel that way and back, just for fun. Okay. Let's give this a try. It worked earlier. I hope it will work now. All right. So this one is in fact much faster than this one, even though it has to go through a longer path. So it's not very clearly intuitive, and to expect that you would deduce immediately the way this curve looks. So to reach from point A to point B the fastest is not that simple. But we can ask ourselves, what would we need to do? Well, obviously, somehow we would have to minimize this point. Because we want the shortest possible time. But this has a problem. We cannot simply calculate this integral unless we already know how y of x looks like. So you can try with some guesses. You can say, okay, let y of x be a straight line, or a arc of a circle, or a segment of an ellipse, or whatever. And then you can plug it in here, see what you get, and try to calculate it. But this does not guarantee in any way that the time you will find is the absolute minimum. You will only find the minimum of your tries, whatever you try. Thankfully, we have developed a method to do this, and this is called the calculus of variations. So what you are studying during your first year and even your second year, I believe, is just calculus. Calculus deals with functions of the type y of x. Calculus of variations deals with forms. This is some kind of a form in which we allow y to change, so the function to change. The point is that if you have something like, let's put some bounds here, t equals from 0 to xf, and then you have some kind of a function here, and we will allow the function to depend on many things. We will allow it to depend on x and y prime, like this. Question is, which f do I have to select to minimize this here? And I'm not going to tell you exactly how to obtain this. This you will learn on classical mechanics, but I will give you the answer. The answer is the f that will minimize this value of t here has to satisfy a special linear differential equation. And the equation goes like this. Like this. This is called the Euler-Lagrange equation, and you will use it extensively in mechanics to solve all of your problems. Euler-Lagrange. Okay, so this step is classical mechanics. Then there is another step which comes from mathematical methods in physics, which shows if f does not depend on x, and in our case, f does not depend on x in any way, then it actually can satisfy a slightly simpler differential equation. I do not know this equation by heart, so I'm not going to write it down. But if f is not a function of x, this simplifies somewhat. After it simplifies, you obtain a final differential equation, and you still need to solve it. You still need to know a way how to solve it. Again, I will not show you exactly how to solve it. I will offer you the solution. You can make sure that the solution works by plugging it in to the equation that needs to be satisfied. And relying on a theorem that's called the unique solution theorem. So if I give you one solution that works, you can be certain that it's a unique solution. There are no other solutions at all. Okay, anyway, to cut the story a bit short, what they knew in the 17th century and what we can obtain now by this entire procedure is that the solution to this problem is a curve called a cycloid. A cycloid is a curve which you can obtain this way. Let's say you have a horizontal plane, and then you have a cycle. A cycle is a wheel. That's why it's a cycloid. That's why you call bicycles bicycles. Okay, so let's assume you have a wheel, and the wheel is moving with a constant velocity in some direction. And you look at a point on this wheel. You fix a point on this wheel. And assume you are filming this with a camera, for example. Everything is in dark. Everything is completely invisible, except this point. This point is shining. It's phosphorescent, for example. And you wonder which curve will be traced out by this point. And the answer is the cycloid. And this curve looks something like this. Well, if it goes that way, then this has to move that way because the center of the wheel moves that way, but it also moves downwards because as this moves, the wheel rotates, and as it rotates, this point at some later time will reach here. You can imagine it rotating this way, which means that it has to move downwards during this period and then upwards during this period. And if you trace out the curve that this does, it looks something like this. Like that. And that is a cycloid. Now, some special part of this cycloid, needs to be selected, where we can put points A and B such that the time between them is minimum. I did not draw this very well. This has to be like vertical here, and this will be our point A pointing vertically downwards, and point B will be somewhere here, not necessarily here, maybe here, somewhere. Okay. What I'd like to show you now is step away from this mathematical nonsense that you still don't know or completely understand, and perhaps a more approachable way of obtaining this result. Well, somewhat. And the idea is this. In the 17th century, people knew about something called Fermat's principle. Ever heard of that? No? Maybe. Fermat's principle states, if I have 2 points in space, so something like this, 2 points in space, and I shine a light beam from one of those points, from A, light will always travel from A to B, assuming it can reach B, in the path that requires the least time. So light always travels somehow, magically, by the path that requires the least possible time. And, well, in flat space, this is simply a line. We know this. This is why we draw rays of light as straight segments, like this. Okay, but what was also known is that in different media, for example, in glass or in water or somewhere else, light can also propagate. It can travel through the medium. but it travels with a slightly different speed than in air or in vacuum. So if the speed here is designated by c, then for example in water, the speed will be c over n. Light travels a bit more slowly in media than in air or vacuum. And the fact that it has to travel more slowly here than in vacuum leads to something called Snell's law. Snell's law, I believe you do know. Snell's law states this. Let us draw a line perpendicular to the boundary between two media. If light is coming in at an angle alpha with respect to this line, then it will not propagate through the second medium at the same angle, but the angle will be different, theta, such that n times the sine of alpha is constant. In this case, c over 1, so n equals 1. And Bernoulli used this idea to try to solve the problem that he posed to other people. The way he did it is this. He said, let's assume we already know what the curve of shortest descent is. Not necessarily described mathematically, but that it exists, certainly exists. So if this is point A and point B, and we have this special curve, what he did is he said, okay, let us pretend that this curve is, how should I call that? Piecewise linear. Okay. Which means it's not actually a curve, it's a collection of straight lines. Something like this. Okay? And why did he do this? He said, let us imagine, as in this experiment, that we shine some light from A. Now this light will travel to B in the fastest possible manner, which is exactly the solution to the problem he is looking at, if this principle is obeyed, and if we assume that the velocity of light is proportional to square root of y. We know that when we have a point that is moving downwards, this needs to be true. We already wrote down 3 equals the square root of 2gy. He only assumed light is behaving in the same way, as if gravity was acting on light. It does not, but as if it is. And let's, for a moment, assume this is true. This means that in this segment and in this segment, light moves at a different velocity. It is as if, let's say, this is the first segment and this is the second segment, like this. It is as if light is somehow hitting the boundary between two media. It's not necessarily drawn like this. What we should do is we should draw a tangent to this curve and then a line perpendicular to it and see how light is reflecting or refracting. But in two different segments, we will have two different velocities. Simply because the average y, this quantity, height, or this vertical displacement measured from A, is different. And then he used this Snell's law, assuming the velocity depends on square root of y. So this gives us something of the form. Okay, so the form will depend on the coordinate system that I choose. I will just copy this from here. It's fine. So it's defined just as we did it. X, Y, the cycloid starts somewhere here, for example. like this. And then a point is selected here. You can imagine a flat segment around this point. And then another coordinate system is drawn here, like this. And a tangent to this curve is also drawn. The tangent of this curve is the approximation of the flat line over there. And we have an angle here, alpha. And what you can show is, if Snell's law holds true, is that V over sine alpha is a constant, just like there. This is true because V equals C over N. So this M can be written as constant over velocity. You remove all the constants, and then you get sine over the velocity is also a constant. And we just flip it around. And we get this. Okay. So the next thing we do is we say V depends on the square root of y, like this. And sine alpha we will somehow deduce from this picture. So in this picture, let's say this is the straight line segment, the tangent to the curve. This is the perpendicular line. Well, this is parallel to y actually. This is alpha. What do I want to do? Something like this. Okay, I'm going to draw a small triangle. When I move in this direction, I move in the x direction. So let us assume I move infinitesimally small. So this will be dx. This thing here will be dy, going from this point to this point. And sine of alpha is, let's see, dx over the square root. So this is the square root of dx squared plus dy squared. Pythagoras Theorem. Something like this. And this is a constant. Okay, so this is another, unfortunately, differential equation. It is the exact same differential equation you will get if you go through the procedure that I outlined earlier, all the way through the end to here, when I said it simplifies. This is what it simplifies to. This can be written in a simpler manner. As you can see here in the denominator, I can take dx out of this square root. So the denominator itself will look like this. This first term will leave me with a 1. And the second term leaves me with dy over dx, which is y primed, squared. And I can cancel dx and dx. And I am left with something much nicer. So instead of this thing, I only have, let's see, the square root of y over 1 plus y prime squared is a constant. If this is a constant, I can also remove this square root, or equivalently, I can just square the whole equation and obtain, let's see, y equals some constant squared.
You forgot to switch out the denominator becomes the numerator.
You're right. Yes, you are right. So this is like this. Okay, so we have y times 1 plus y prime squared equals a constant. Okay, again, the solution to this equation is the cycloid. I'm going to write down the equation for the cycloid. The cycloid is given by a parametrization something like this. X is h times t minus sine of t, and y of t equals h 1 minus cosine of t, like this. If you would like, well, we have 10 minutes. I have just a few more things to show. We can even check if this is true. If this is what we assume is the solution, satisfies this equation here. How do we do that? Well, okay, we already have y. Y equals h times 1 minus cosine of t. But here I have 1 plus y prime squared. Note, y prime is dy over dx. We do not have y written as function of x. So what do? Is we expand this fraction. I write like this: h times 1 minus cosine of t, 1 plus, and instead of dy over dx, I will say dy over dt. Note, t is not time. T is just some dummy variable. Doesn't mean anything. In this case, in this specific case, okay? So instead of dy over dx, I will write dy over dt and then dt over dx. Squared. Because this I can calculate. Dy over dt. So the derivative of this function with respect to t is h times, and then when I derive the cosine, take the derivative of the cosine, I get a minus sign, which cancels with this minus, and we get h times sine of t. Dt over dx, this is the same as dx over dt to the power of minus 1. So we can find dx over dt. So this will be h times the derivative of t is 1, the derivative of sine of the cosine, so I have h times 1 minus cosine of t. And plugging it all in, we get, let's see, h times 1 minus cosine of t times 1 plus dy over dt. This is up. Let's do this, open parenthesis, h sine t. Dt over dx is the inverse of this here. So it's 1 over h times 1 minus cosine. Like this. H and h cancel out. We can find a common denominator here.
Professor, a square.
Square. Yes, thank you. So let's see, this is 1 minus cosine of t squared. So we'll put it in the same denominator. This 1 will become 1 minus cosine of t squared plus sine squared of t. Like this. So this cancels out this. And then we have to hope that the numerator and the denominator also cancel out, as they do. So 1 minus cosine t squared, let's do this on the side, plus sine squared t. This is 1 minus 2 cosine t plus cosine squared t, and then plus sine squared t. We can use the trigonometric identity. Cosine squared plus sine squared of any number is 1. 1 plus 1 is 2. I get 2 minus 2 cosine t. I take out the 2. And 1 minus cosine t, 1 minus cosine t cancel out. And I am left with 2h on the left side. Which indeed really is a constant. So this works. This is our curve of fastest descent, not the shortest, but the fastest descent. And what is remarkable is that when people found this to be true, they were kind of amazed because they already knew another special property of the cycloid. So what we showed now is the cycloid is the curve of fastest descent. But what was known earlier, that it is also a curve called Pythagoras or isochrone. And this is another very, very special property. And it goes like this. It has to do with pendula and general physics 3, where we study oscillations and waves. So what you might know is that if I construct a mathematical pendulum like this, I displace it from this vertical position, right? Let's say here, and then case B here, and then measure the times required to reach from A to O and the time required to reach from B to O. And I will find that these times are not the same. So, for the mathematical pendulum, what we call the period of oscillation, in fact, depends on the initial angle theta. I know this is not what you learn in school. In school you say, oh, the period is constant. The period is this formula here, right? No theta in it, but this is false. This is true only if theta is small. So for example, if I displace this by 1 degree or by 2 degrees, I'll always get more or less this period. But if I displace it by 20 degrees, then I will get a larger period. Not just slightly larger, much larger. And this was a problem in the Middle Ages because these things were used as clocks. You didn't have better clocks. Well, you did, but they were too expensive. So the question was, is it possible to construct a pendulum such that no matter where I started from, it always has the same period, always. And this property of always the same period is called isochronicity. So it doesn't matter where you start from, always the same. And the answer is yes, it's possible. And how is it possible? We have to make sure that the curve traced out by this point mass or B. It's not a circle. In this case, it's a circle, right? It's a constant length. But we have to make sure that the point traces out a cycloid, which is similar to a circle, but not quite. So it has to look like this, approximately. And then the question is, but how do we achieve that? And the answer is, you have to find a special way to shorten the length of this pendulum such that this will trace out the cycloid, right? And the way to do this is by making something that has two cycloids in itself, which again is a coincidence that a cycloid will produce a cycloid. This is not true for other shapes or curves. But if you do this, and then you place your bob here, then as you move the bob this way, this vertical line will touch this part here, and this, for example. And in effect, the length will be shorter, right? Like this. So the length shortens as you move it out from the equilibrium point. We have such a pendulum here. I had a student 3D print it, and there is a very small lead bob here. And we indeed made sure that no matter where you start the bot from, it can be very close to the equilibrium point, or it can be all the way here. Always takes the same time to go through a full period. And we even use this property to measure the constant g in Zagreb. So the acceleration of gravity. And I believe this is the most precise measurements done in the last ever in Zagreb. So we obtained g up to 6 decimals, I think, with the error, significant error on the 6th decimal. Okay, the problem of isochronicity we'll leave for General Physics 3, but just so that you know, the curve that we obtained here and the curve that we will obtain there are two and the same. Okay, sutra u 12, jel tako? Da? Sutra u 12 vidimo se. Yes, da.